welcome to the University of Urbino. Togliamo la mascherina. It's a pleasure to have you here. We are here to award two colleagues, Professor Victor Bampuccian and Vincenzo De Risi. They are being awarded by the Comandino Medal and the Del Monte Medal. These two medals are assigned on the basis of their work on history of science and fundamentals of science. And we are very happy that we are able to do it in present this year. And so these are the awards that were supposed to be assigned last academic year, 2021. Let me read the two motivations for their work. So the first medal has been assigned to, again, Professor Victor Bampuccian, and for his contributions to the comprehension of the foundations of geometry, through which he highlighted new and important results, often turning an explored path into fertile grounds for research. Thank you. And the second motivation is for the on which has been based the awarding of the second medal to Professor Vincenzo De Risi for his contributions to a rigorous analysis of the concept of space and its historical and theoretical development, and for the advancements he made possible on the comprehension of ancient and modern geometry. Thank you. So, Professor Laerte-Sorini, the floor is yours.
I'm very pleased to represent the Center of Studies Urbino e la Prospettiva, especially on this occasion in which two distinguished professors such as Victor Bampuccian and Vincenzo De Risi are awarded. As you know, it is the 600th anniversary of the birth of Duke Federico, and this mainly thanks to his clever contribution. If today we can talk about Federico Comandino Medal and the award destined for career development, and Guidobaldo del Monte Medal, which is intended for young researcher, and an ideal line between master and disciple. In fact, Duke Federico has the intuition to create a place similar to a crossroad of art and knowledge, a meeting place between art and science, a place in which new forms of art were born. Our Center of Studies has a 20-year history during which it has the audacity to follow the Duke Federico's legacy by promoting knowledge, organizing conference, film review, seminars on the subject of science. And this dissemination within the center, we also publish a prestigious review of book. We won national and international projects such as Formelle of the Ducal Palace of Urbino, one of the best Italian-founded projects, and we organize international exhibitions such as the one entitled Sapientia, Pietias et Otium al Tempo del Duca Federico, which will be inaugurated on June 4 at the Albani Museum, and we give a prize such as those we are assigning here today to Victor and Vincenzo, who join the list of well-known colleagues already awarded, such as Reviel Ness, William Renechea, Enrico Gamba, Sir Roger Penrose, Jürgen Rand, and many others. The mission of the center is today confirmed in creating a network of people and disseminating their common knowledge with an activity of public engagement impacting on social welfare. Thank you all for being present, and long life to the Center Urbino La Prospettiva. Now, Vincenzo Fano.
Thank you very much, Laerte. I am here bringing the greeting by our head of the Department of Pure and Applied Sciences, a department in which science and history of science, philosophy, logic are together. It's an interdisciplinary department here in Urbino. We are very happy of having here in Urbino this department. And Urbino was in 16th century a place where Federico Comandino and Guido Baldo, two very distinguished scholars, build a sort of bridge between humanities and science that is also today living. Federico Comandino and Guido Baldo were scholars, very good mathematician and physicist, at the same time also very good scholar in ancient literature. They are able to understand Archimedes, Euclid, and so forth. So they brought in the modernity, the thinking and the work of this very important scientist of antiquity. From Guido Baldo and Comandino, Galilei take the step and begin the scientific revolution, a very important event in the general history of Europe. So in Urbino we have these two medals, and I am very happy that two medals, one for the career, one for the early career in history of science here in Urbino, and I am very happy that Jan Pambuchan, that is now our visiting professor in Foundation History of Geometry, and Vincenzo, that was before the pandemics visiting professor, also with us for many months in Urbino, giving courses in history of science. I am very happy that both received today this important recognition on history of science, and I hope that this discipline will be more and more important in our university. Thank you very much.
So thank you very much. And well, most of all, thank you for the medal at the University of Urbino and the friends and colleagues here. It was really an honor and a pleasure, and I'm really moved by this award. I'm really happy. I was here, as Vincenzo was saying, for a month in 2017, and I must say, I mean, this was really one of the most exciting months and most pleasant months of my academic live, so I'm very happy to be here again, and I'm happy that you are still managing to have this incredible meeting between scientists, mathematicians, philosophers, historians, which is really a richness of the university, and I'm happy that you have established this medal dedicated to Guido Baldo for young scholars. I mean, I'm a bit borderline, but I think this is really important for the community to have an important award for history and philosophy of science and mathematics for young scholars as well. And I am also happy that it is dedicated to Guido Baldo, and I hope that this would move things a bit in order to study more Dal Monte, who would, in fact, very much deserve a better history and a better consideration by historians. So I will give a talk on history of mathematics, and I will say something about diagrams in mathematics and in geometry. Diagrams, that is to say, figures, pictures that you find in geometrical books, triangles, squares, and things like that. There is a flourishing literature, in fact, in the study of diagrams in mathematics in the last decades. This mostly concern cognitive scientists, philosophers of mathematics, and of course, people working in computer science, attempting to understand how diagrams and images and drawings are used in geometry in order to draw mathematical conclusions. What is still lacking, I think, is a bit of history of this phenomenon. That is to say, all these studies which are very important on diagrammatic reasoning and visual thinking in mathematics, are still considering geometry mostly as one thing with no historical development. And I think that here we as historians of mathematics should still say something, and that the history of diagrammatic and visual thinking in mathematics is really important. And so I will try to give you some hints of this vast territory, which is very much to be explored yet. And I will begin by making reference to something that Enzo said, that is to say, the connection between geometry and the conception of space, which is my main topic of research since many years. That is, now we are all used, in fact, we have heard Victor's talk as well, to consider geometry as somehow connected to the notion of space and to consider geometry as the science of space. But this was not the case for many, many centuries. In fact, if you take ancient geometry and you look at Euclid or medieval geometry or Renaissance geometry, you will find that no one among those geometers or philosophers of geometry mentions space at all. I mean, classical geometry was a geometry of triangles, of circles, of squares, of conic sections. That is, individual figures of which we want to understand the properties and the features, but they were not conceived as embedded in any kind of space, and much less spatial properties or space itself was considered to be an object of geometrical investigation. And the transformation of geometry from this kind of science of figures, of individual figures, into a science of space happened, in fact, very late. And I think I found, in fact, that the first person who ever claimed that was a philosopher, a Neoplatonic philosopher, more or less contemporary of Comandino and Guido Baldo. This Francesco Patrizzi da Cherso, who lived here in Ferrara, not far from here, and Patrizzi wrote two important books on the metaphysics of space called De Spazio, And then he added a third book called Della Nuova Geometria, written in Italian. And in this book, for the first time, he stated, as you see, le matematiche tutte principali e subalterne né si astraggono dalle cose naturali, which would be Aristotle, of course, né sono nella fantasia, which would be the Neoplatonic tradition of Proclus and the other, né nella dianea, Plato, ma lo spazio è generale loro subjetto. That is, space is their proper subject. And this is, I think that I know, the first statement in which someone say that space has something to do with geometry, and it is in fact the object of geometrical investigation. In the following centuries, that is in the 17th century and then in the 18th century, this idea by Patrizi became widespread, and more philosophers and mathematicians began to accept the idea that geometry is in fact the science of space. But it came to general acceptance only in the 19th century. So this is the big background, that is the history of the notion of space intertwined with the notion of geometry. And I would say that this very general history offers a very important framework to understand the development of diagrammatic reasoning and visual reasoning, something that apparently has not much to do with this, but that in fact, it is, I would try to show, deeply connected with this philosophical development. So let's begin to talk about diagrams and pictures in geometrical books. Geometrical texts have this kind of diagrams since the beginning. You have here one of the most ancient papyri on geometry, containing a section of the elements of Euclid, and you see there are diagrams here, there are pictures here. You have some manuscripts in Greek with the elements of Euclid. You have some very nice medieval editions of the element with colorful diagrams and beautiful drawings. You have some others here, very nice codes. And you see here again, these are circles and triangles as in Euclidean tradition. You have mathematicians that, of course, work with diagrams in their private notes. And this is Comandino from a manuscript from the library here in Urbino. And you have, with the invention of the press, printed diagrams and very complex diagrams, which began to be printed in the 15th and then in the 16th century. And this is an important part of the story. And it is also an important part of the story of Comandino himself, because of course, to do this kind of printing, one needs to mobilize a lot of people doing this drawing for the print. Then you have any kind of diagrams in the early modern age, diagrams which have no letters, but rather names. You have diagrams in black and white in order to stress different parts of the figure. You have diagrams in 3 dimensions, as you see there on the right, in order to describe 3-dimensional figures. But you also have books with pieces of paper that can be constructed in order to touch and see what 3-dimensional figures are. And then you have diagrams which are colorful and can be employed, as you see, in the demonstration itself, just comparing parts of the drawing from the diagram itself. And here we have reached the 19th century. So what I would like to say is that you have historically an enormous variety of diagrams evolving from the first manuscripts or papyri on Euclid to contemporary times. And of course, one may use these diagrams for a lot of different uses. And what I'm stressing is that we still need a history of this changing phenomenon. On the one hand, it is quite understandable that we do not do a history of that. Because if you take the oldest diagram here, and then you take Hilbert's diagrams from the Grundlagen in 1899, you see that, I mean, not much seemed to have changed after all from the first to the second book. And so I think that many philosophers of mathematics and philosophers of science in general just draw the conclusion that more or less this was a kind of stable practice throughout centuries. Well, we know on the other hand that this was not the case, because as we all know, one of the most important features of Hilbert's approach to geometry is that you do not really need the diagrams for your own demonstrations. That is, in principle, you could read, or you should be able to read, the Grundlagen geometry without pictures and try to understand what is going on there, because you have definitions enough, axioms enough in order to follow the proof without looking at the diagrams themselves. And this is not the case of Euclid. This is not neither the case of Euclid, nor the case of many, many other treatises of ancient, medieval, Renaissance, and early modern geometry. In these works, you rely on diagrams in order to make inferences. And this is the epistemic value of diagrams. It is why you can do things with diagrams and you can prove things with diagrams in classical geometry. So at least there has been this important change. Let's see this a bit closer. Let's take the most classical proposition of the elements. This is the first proposition of the elements, where Euclid teaches on how to draw an equilateral triangle on a given segment. This proposition has been commented over and over throughout the centuries, because it became a kind of paradigm of a geometrical proof. And the most important thing and striking thing of this proof is that Euclid employs, in order to carry out this proof, a lot of principles and a lot of statements. That is, you have that segment there. Then Euclid employs an explicit postulate allowing you to draw circles from any center and any radius, and through that he can draw the circle. Then he uses this postulate again, and so he can draw the other circle. Then he uses another postulate, postulate 1, allowing to draw a line from any point to any other point, to draw that line here. Then he uses again postulate 1. Then he uses a definition of the circle, saying that the radii of a circle are all equal to one another, and in this way he establishes that in the figure that he has constructed you have two equalities, AB is equal to AC and AB is equal to BC. And then he goes further and uses another principle yet, a common notion 1, saying that things which are equal to the same things are also equal to one another, and he concludes with the third equality, and then he can say that ABC is an equilateral triangle. So you see, in order to perform this absolutely trivial construction, he uses two postulates, one common notion, one definition, and it is very explicit that everything is going through this kind of explicit principles. Yet, as you know, modern mathematicians had something to say about this proof, and in particular, they say that Euclid has no explicit principles in order to say that when you draw these two circles, one centered in A and the other centered in B, they will actually meet in a given point C. Perhaps the circles are not continuous enough and there is some gap. Perhaps they meet, but they do not meet in a point, but in a line. Perhaps they are apart, because if you are imagining not to look at the diagram, it might be that these two circles are just too distant from one another in order to intersect. So what Euclid is doing here is clearly relying on the diagram, on the image, on the picture, in order to draw the conclusion that these two circles have, in fact, a point of intersection in C. That is, when you draw them, they have to intersect. When you actually perform the construction and you look at the diagram, you see that they cannot but intersect in point C. Now, this kind of practices we call generally now diagrammatic inferences. That is, there are inferences that are not drawn by explicit propositional principles, but rather from looking at the picture and the diagram. So what is happening in classical geometry is that you have a kind of interplay between a propositional part of the proof and a diagrammatic or visual part of the proof, which gives you some further information that you make use of in the proof as such. And modern mathematicians, that is Hilbert, criticized this kind of diagrammatic inferences, saying that, abiding to a completely different ideal of proof as something that should not use this kind of visual hints in order to prove things, but should be entirely propositional or symbolic, but in any case, entirely propositional. Now, some philosophers of mathematics nowadays have attempted to show how did it happen that, notwithstanding the many criticisms that modern mathematicians have raised against the use of diagrammatic inferences in classical geometry, you do not normally find any mistake in classical geometry. That is, demonstration in classical geometry do rely on diagrams. Modern mathematicians tell you beware of diagrams, because if you do inferences just looking at the figure, you may go wrong. But nevertheless, the classical texts of mathematics do not have any serious hindrance in looking at the diagrams. And in particular, Kenneth Manders from Pittsburgh has advanced a very popular and important theory in the 90s, according to which it is useful to distinguish different properties of geometrical figures, and stressing that some properties can in fact be inferred from diagrams and drawings and pictures, and some other properties cannot. And that Greek geometers and medieval and Renaissance geometers were in fact following this kind of distinction between things that can actually be proven from diagrams and things that cannot. So for instance, when you take a Pythagoras theorem, you cannot infer just from the diagram that the big square is equal to the sum of the two other squares. It is not valid to look at the diagram or even to measure the diagram and say, see, this is true, so Pythagoras' theorem is true. These are what Ken Manders call exact properties. That is to say, these are properties that concern measurement, and everything that concerns measurements, you cannot infer this kind of properties just looking at the picture, because they concern exactness and measuring things. On the other hand, if I draw by hand the diagrams of Euclid 1.1, no matter how badly I draw the circles, I will see that they do overlap and intersect in point C. So there are some other properties like this that are really unaffected from the fact that I am working with symbols and imperfect diagrams rather than real geometrical figures. So what Manders is saying is a kind of revival of Poincaré's famous definition of geometry as reasoning well from badly drawn figures. That is, you can do that. And so the claim is that even though ancient geometers, of course, or epistemologists did not spell out this distinction, nonetheless, there is a constant practice according to which all the properties concerning measure are always propositionally inferred, And all the properties concerning this kind of relative position of things that are unaffected by small modifications of the diagrams, they are diagrammatically inferred. In fact, this point of view of Kenneth Manners works quite well from a historical perspective. That is, if we look actually at what Euclid, Apollonius, Archimedes, but then also Arabic mathematicians in the Middle Ages or Renaissance mathematicians in Italy or in France were doing in the 16th century, for instance, you see that they follow quite well this path. And of course, I have shown the case of Euclid 1.1 with the intersection of the circles, but there are many, many other properties that are diagrammatically inferred, such as, for instance, order properties and so on, that Euclid did not axiomatize, but always see in the diagram. Now, at some point, though, we have seen mathematicians began to be suspicious about diagrammatic inferences. So the question for us as historians is, why did it happen? That is, why a practice of mathematics that was going so well with diagrammatic inferences at some point transformed, as an ideal at least, into something entirely propositional, entirely logical, if you want. And the standard answer here is that it depends on a kind of crisis of intuition in the 19th century. That is, in the 19th century, mathematics became too abstract and too remote from intuition that you could not rely anymore on diagrams. In non-Euclidean geometry, you cannot always rely on what you are seeing. In abstract algebra, of course not. In set theory, when you deal with infinity, much less. In complex analysis, who knows, and so on. And for this reason, 19th century mathematicians began to develop purely propositional technique in order to deal with geometry. And this was the beginning of what Hilbert and other in the 20th century began to say. Now, I would not deny all of this, of course, but if you look at the historical text, this doesn't work really well. And this is, I think, an important point. That is to say, doing mathematics without diagrams and without diagrammatic inferences began much earlier than the 19th century, much earlier than the discovery of abstract algebra or non-Euclidean geometry or anything like that. It began, in fact, in the early modern age. In the early modern age, you have several mathematicians and several epistemologists that began to question the fitness of diagrams to provide rigorous demonstration in geometry. You have people like Pietro Catena, who involved in the question of the certitudine mathematicarum, said that diagrams are the hocus pocus of mathematicians, just a trick. You have John Wallis, who in attempting to prove the parallel postulate has long paragraphs against the possibility of drawing inference, just looking at the figure. Then you have, for instance, there is an important book on perspective written by Guidobaldo Dal Monte, you know, the Perspectiva Libri Sex. Now, this Perspectiva Libri Sex by Guidobaldo are full of pictures, are full of images, but they are somehow reused in 1715 by a British mathematician called Brooke Taylor, who wrote this linear perspective, which draws a lot on the work on the mathematical work of his predecessors and Guidobaldo himself. And this is an entire book on perspective without figures, without diagrams. That is, you have a mathematical treatment of something that should be of use for painters artist that just has no images whatsoever. This was a very strange book, and it was also an editorial flop. No one bought it, and at some point, Brooke Taylor wrote a second edition with a lot of pictures that sold very well. But in the preface, he said, "I have to apologize with the reader because I had to put images in there, even though the mathematical treatment would not need any of those." So you see that something was happening between, let's say, Guidobaldo's purely mathematical treatment of perspective in 1700 and what Brooke Taylor was doing a century later. You see something similar also in different disciplines. Once again, if you take the treatise on mechanics by Guidobaldo, this is full of pictures, and Bertoloni Meli has written a wonderful paper showing that many of the theorems on mechanics proved by Guidobaldo are in fact proven by inspecting the diagram, the figure. That is, there is no real articulation of the proof. It is just, look here, you will see that this is true. And many of these theorems were used later on by Lagrange, who quotes Guidobaldo, in fact, in his Mécanique analytique. And this Mécanique analytique, of course, it is very famous to be a book on mechanics without figures and without images. So once again, something happened in the course of the 17th century or in the 18th century that brought a radical shift on what counts as a good demonstration in mathematics, in mechanics, in geometry, on the one hand with diagrams, on the other hand without diagrams. So for instance, take our proof of Euclid 1-1. You find normally in histories of mathematics that the one who detected the fact that there is a gap in the proof of Euclid and that Euclid had to provide some principle for the intersection of the circles there was Maurice Pache in 1882. But in fact, this is not the case. For this kind of gap in Euclid was detected much, much earlier. In fact, it was detected by this Ronsfine or Ronsfinet in 1532, who said that that proof had a gap, and he inserted a sixth postulate in the elements of Euclid, saying that if a straight or curved line is drawn from a point which is within a figure to another point in the same plane which is outside of the figure, it will intersect the sides of the boundaries of the figures. Through these purely propositional axioms, you can, in fact, give a demonstration of Euclid 1-1 that can show that there is a point of intersection in C, something that was not done by Euclid. So Fien did not need to rely on the diagram in order to draw this kind of inference. And this axiom by Fien was extended by a Spanish scholar, de Monzon, who used it, then by a French scholar, Claude Richard, who had several axioms to this effect, that is to ground a theory of intersection without diagrams. Claude Richard, by the way, has this edition of the elements of Euclid, but he also has a kind of commentary on the elements of Euclid, which has remained in manuscript form, and you can find it in the Library of Madrid. And this passage here is Richard's proof of Euclid 1-1. You see that there are no pictures in the manuscripts. That is, Richard went on with a completely only propositional reasoning that made without any diagram there. And then you have further and further others employing this kind of axioms in the 17th century: Wallis, Pascal, Borelli, Schott, Robert Wahl, and of course Leibniz, who wrote a lot of important papers, also from the methodological point of view, saying that you should not use diagrams in geometry. So you have this important change that many mathematicians in the 17th century, in the 16th already, but especially in the 17th century, began to regard the diagrammatic inferences as not valid, not rigorous. And of course, here we have an important historical phenomenon to explain, because this could not be due to any true abstract mathematics. There were no Euclidean geometry here, no complex analysis, nothing. I mean, this was just classical Euclidean geometry. But nonetheless, there was an important change in the foundations of geometry and an important change in the ideal of proof of geometry. And so I think here we can reconnect the story about space that I mentioned at the beginning of the talk, because at some point I just asked the question of which mathematicians attempted for the first time to write an entire treatise on geometry without diagrams, without figures. We have seen that there are several mathematicians who accepted one or, I mean, who added one or the other axioms and therefore made non-diagrammatic, transformed some propositions into non-diagrammatic proofs. But who is the first who embraced this as a kind of research program and with the idea of writing an entire book without diagrams in geometry? And I mean, I went back and back, and with my great surprise, it was again Patrizi's Nuova Geometria. This is something that I did not expect, frankly. I mean, if you read Patrizi della Nuova Geometria, you find that he only has propositional proofs and no use whatsoever of diagrams. And this is explicit in the preface of the book. He doesn't want to use this kind of diagrams. Patrizi's proofs are very bad, I must say. That is, if you read them, they are kind of logical inferences which are very abstract and that do not really provide any interesting mathematical or geometrical content to what is attempting to prove. So we can say, in a sense, that what Patrizi was attempting to do was not only impossible from a logical point of view, but also full of mistakes from his part. That is, he managed to prove the entire first book of the Elements of Euclid without diagrams, just because he assumed things without noticing and made a lot of paralogisms and other mistakes. Leibniz himself, who was in the same epistemological program of proving the whole of the Elements of Euclid without diagrams, read Patrizi's book, and he commented that the preface is wonderful, that is, the program is wonderful, but the les dedans fait pitié, the interior of the book of Patrizi is just a waste of time, because Patrizi was not able to do what he was set to do, that is to say, to do geometry without diagrams. But at this point, you see, the fact that the same person that I mentioned before as the first philosophers who claimed that geometry is the science of space is also the first philosophers, the first geometer that said that we should do geometry without the consideration of diagrams. It is an important clue. I mean, it is something that should speak a lot about the connection between philosophy of space and the epistemology of diagrams. And what I think that happens is that this allows us to answer to the question, how did change mathematics? How did mathematics change in the early modern age so that the ideal of proof was changed into something purely propositional? Now, let's go back to the distinction that Ken Manders drew between properties of the figures that can be proven propositionally, that is about magnitudes, about measure, and properties that can only be proven by looking at the diagram itself. Now, if we consider which was considered to be the object of geometry before the early modern age, that is, geometry was about circles, squares, triangles, conic sections. All these figures were generally called by Greek mathematicians and philosophers magnitudes, that is, megete. And this immediately shows that the main aim of classical geometry was, in fact, to measure things. And this is a big part, of course, of Archimedes and the elements of Euclid, that is to give exact measurement of different figures. And if you think that the main object of geometry are magnitudes, then it is clear why in the propositional part of the proof, when you are explicit, when you, as mathematicians, write down step by step, what are you doing, you are dealing with magnitudes, you are dealing with measurements, you are dealing with this kind of things. That is, you are thinking that geometry is about magnitudes and you describe everything that happens with these magnitudes in your deductive system. On the other hand, you do not have the idea that space is an object of geometrical investigation. Therefore, properties such as to be on the right or on the left on that line, beyond the circle or inside the circle, in between these or that, or to overlap, or things like that, or being continuous, are not properties that you are considering explicitly in your demonstration. You are not doing your demonstration thematizing this kind of properties. You deal with magnitudes, and then you look at the diagram in order to draw these other properties. So the properties that Kenneth Manders called the non-exact properties, I think that from a historical point of view, it is useful to call them spatial properties. They are properties concerning spatial relations, being here, there, beyond, in a certain order, continuous with, etc. And so the idea is that classical geometry only concerned magnitudes, and diagrammatic inferences concern spatial properties. What happened in the early modern age is that space began to be taken and thematized as the object of geometrical investigation. Now you are investigating not magnitudes, but space and spatial properties and spatial figures. And at that point, you begin to put in propositional form things about space. That is, you began to write down what happens when a point is on one side or the other side of a segment, or inside or outside of a circle, or when two circles do intersect or do not intersect. That is, you are pointing your attention, your propositional attention to this phenomena here. And so you find, for instance, that in Pascal, the introduction to geometry by Pascal begins by saying the object of pure geometry is space. So you find a very important statement there. And then just a few lines later, a circumference passing through a point inside of a circle and the point outside it, it intersects the circumference of the circle at exactly 2 points. This is a new axiom, of course, concerning space. And the connection is quite explicit in this kind of axioms. So what I would like to say is that this transformation of geometry from a science of figures into a science of space led led geometricians to thematize spatial properties. They were therefore expressed propositionally in proof and in axioms, of course, because at that point you need axioms as well. And geometrical diagrams were slowly abandoned as the as a viable way to do geometrical investigation. And in fact, Patrizzi and then Leibniz were probably the two most important figures in the early modern age, thematizing space as the object of geometry and being not just mathematicians, but also philosophers and epistemologists, saw this very well and explicitly stated geometry is about space. Geometry should be done without diagrams at all. And at that point, however, you get a kind of reversal of the classical narrative, according to which geometry was de-diagrammized in the 19th century. It is not that in the 19th century there were new necessities for mathematics, that is, non-Euclidean geometry, etc., that forced you to abandon diagrammatic inferences. We can see the thing on the other way around. It is since from the 16th century or the 17th century, mathematicians were trained more and more to do geometry, Euclidean geometry, perfectly intuitable geometry, without intuition, that is to say, without looking at the diagrams, because they were more and more pursuing a programming geometry according to which the ideal of demonstration was purely propositional, that at some point in the 19th century, one could invent non-Euclidean geometry and say, do not look at the diagrams of everything, just follow your reasoning and you will find this kind of things, even if your senses say you something different. And it is that kind of training and that kind of transformation that produced the 19th century 19th century revolution as a kind of consequence. I can perhaps just say a little bit more. That is to say that it is important to understand also that a diagram is a kind of intentional object. That is to say, what you are doing with a diagram is what really matters, not the figure on paper. And what happens often in the early modern age is that you still find diagrams in mathematical textbooks, even though these diagrams are not used in the demonstration itself. That is, you can follow the demonstration without looking to the diagrams, but nevertheless, the author puts the diagram there. Because of course, diagrams may have a lot of different uses. And we have seen Hilbert himself put diagrams in the Grundlagen der Geometrie, because this is easier to follow the demonstration. It has a didactic value, an epistemic value, which is not in the proof, but it is nonetheless in the comprehension of what is going on there. So in Patrizzi's book, for instance, you do find diagrams. You find that kind of diagrams have no letters. They are not referred in the proof. They are just put there in order to make you understand what is going in the propositional part of the proof. And Umberto Eco, in the Trattato di Semiotica Generale, says that there is a common thing in semiotics, that some signs are first used as icons in order to draw conclusions, and at some point they are considered just as symbols, that is to say, as useless things from the epistemic point of view, and having only a kind of explanatory intent. So what is happening, and Eco calls this the stylization of icons. I think we can apply this concept of stylization to diagrams in the early modern age. So what happens is that in some texts, they just disappear. And in some other texts, they remained there, but in a kind of stylized version, in the sense that they were not employed in the proof, but they were just there in order to illustrate what was going on. So for instance, this diagram from a medieval treatise is clearly just an illustration, because you are not performing any theorem there. This diagram from Comandino is an icon. That is, you are using this diagram in order to perform the proof. If you have not this diagram, Comandino's proof would not work. This diagram, very similar, by Borelli, is not an icon anymore, because Borelli's text does not refer to this diagram, and there is no use for him for the diagram itself. So you have these three diagrams, and you see the first and the third are similar as far as their use is concerned, because they only illustrate things. The second one, the one by Comandino, is the real diagram that matters in the demonstration. So you see, you have a kind of evolution of, you have an evolution of the way in which you look at diagrams, even though they may remain similar throughout the centuries. So it is an important history, I think, in order to see how the material support may remain the same, but nonetheless, the intentional value of what you are looking on, what you are doing with diagrams is changing. And so all these images of Euclid 1.1 have very different values from an epistemological point of view, because some of them are used for demonstration, some are not. Some are used for some demonstrations and some for some other demonstration, and so forth. So this was more or less the story that I wanted to tell you. We do need a history of diagrams in mathematics and in epistemology. And there is a lot still to do, and this history has important epistemic consequences, because it deals with the ideal of proof and the very notion of what is a demonstration and what is valid as a demonstration. And at the same time, we see that this story is quite complex. It cannot be just dealt with a story before the 19th century and after the 19th century, and rather it has a lot to do with the notion of space and the philosophy of space, which comes from a completely different perspective. Okay, thank you very much.